Hello. It is still November. The heat just kicked on, but I don't care. And today I'm going to make my car charging station boil water very quickly. And I'm going to do it using this British kettle, which I have made work with a car charging station using this very cursed adapter I built using very cursed parts. Now, before I hear any complaints about the effort that got put into this one, this video is basically a repeat of that time I made a shop heater with a J1772 connector, allowing me to use my car charging station as a nice and convenient power cable that delivers 240 volts AC, which, in case you didn't know, is all a level 2 charging station actually does. But this time I put that connector onto an electrical box, and on the other side of it is this horrible thing. But more on that later. You might wonder why I've done this. Well, you see, I have a few British friends who have all expressed frustration at how slow electric kettles are here in the US. Because of our 120 volt household power and the desire to maintain compatibility with smaller 15 amp circuits, most ordinary appliances are limited to 1,500 watts of power, and kettles are no exception. Put that much power into a liter of room temperature water, and it will take about 4 minutes for that water to boil. Now, personally, I think that's plenty fast, but because the Brits have 13 amps of 230 volt power at every receptacle, they can shove 3 whole kilowatts of power into their water boily things. And because they can, they do. And today, they're so used to this that the absurdity of a plastic countertop appliance sucking down more power than my home's central air conditioner just doesn't quite register. Fun fact, the BBC used to have to share when breaks in their programming would happen with the national grid, because 500,000 people getting up to put the kettle on all at the same time meant there was suddenly a large nuclear reactor's worth of power draw to be dealt with. For making tea. And other hot beverages, probably. Ooh, maybe even porridge. Anyway, after I made that video on the shop heater powered by my charging station, a certain slow-mo guy named Gav suggested I make a kettle that works with a car charger. That sounded delightfully up my alley, so I promised I would make that happen. And here we go! First, I would need to get my hands on a kettle designed to work with the 240 volt electricity my car charging station puts out. So I imported this British kettle, which draws the customary 3,000 watts from the wall. Next, I would need a way to power this kettle from my charging station. Now, I could have done the sensible thing, which would be to build an adapter like this, with a NEMA 620 receptacle, and then cut the end off of this cord and connect it up to a NEMA 620 plug. But a while ago, someone on the internet made me aware that Leviton sells this thing. Yes, this is a real product you can buy for some reason. The Leviton BSRDP-W is a single BS1363 receptacle designed to fit into a North American junction box. Why on earth do they sell this? I have no idea. There's no way this would be to code anywhere you might install it. Okay, so this instruction sheet made me dig a little deeper, and it would seem that Saudi Arabia's current SASO standards call for Type G plugs and sockets. That's the British one. But it seems that in the past, they and/or perhaps other Gulf countries were following NEMA standards for junction boxes, etc. This device meets SASO standards, and that little symbol above the 0007 is the Gulf conformity mark of the Gulf Cooperation Council, and so I think it is intended for use in retrofit situations in those countries. So it's got a real use case, but certainly not here. Because we use split phase power over here, nothing you might plug into this will be correctly wired. It will function just fine, no electrical load knows the difference, but these 2 pins will both be live at 120 volts potential to ground, which means depending on how a device was wired, it may always be energized even if switched off, which might be shocking. Now, Leviton was smart enough to make sure this switch is a double pole switch that isolates both pins, but still, this is all kinds of weird. And yet, it exists. So I threw together this adapter, which simply has the line 1, line 2, and ground pins of the J1772 connector wired directly to the cursed receptacle on the other side. Am I showing you what's inside of here? No! And to make the charging station think it's plugged into a car which is requesting power, the control pilot pin is connected to the ground pin through an 882-ish ohm resistor and a diode. Now, plugging this into my charging station causes it to go clack and energize this receptacle with the correct voltage, but in the wrong way. It will work though. So let's do a little test. Here's an American kettle plugged into the wall and bringing this much water to a boil. This is almost exactly 1 liter, but not quite. The important thing is I'm using the exact same amount of water with every test. The water was 63.7 degrees Fahrenheit, or 17.6 Celsius, and with the kettle pulling about 1,460 watts, it took 4 minutes and 5 seconds to hit my subjective definition of boiling. And for a slightly less subjective definition, the kettle switched itself off at 4 minutes 17 seconds. But I had a second American kettle to test. This cheaper model has an exposed heating element, and since it becomes completely submerged when filled with water, there are absolutely no heat losses to the air below the kettle. That doesn't matter very much, but you'll see why I also tested this one later. This one was filled with water at 63.1 degrees Fahrenheit, or 17.3 Celsius, and after a failed start because it wasn't seated properly, it drew 1,420 watts from the wall and required 4 minutes and 15 seconds to hit my subjective definition of boiling. And it switched itself off at the 4-minute 35 seconds mark. So both of these kettles require about 4 minutes of time to boil about a liter of water. And now it's time to see how much faster a right proper kettle is. This time, the water was at 61.8 degrees Fahrenheit, or 16.6 Celsius. And I want you to notice something here. This is just under 1 liter of water, and when I placed it in this kettle, the water line went up to about the 4.5 mark. That doesn't make any sense, so this is 4.5 what exactly? Oh, I found the answer, and having found it, I simply cannot resist pointing out that every kettle I have ever used here in the US tells you its capacity in liters. Yet, this British kettle has markings for, and I swear I'm not making this up, breakfast cups. Not an ordinary British cup, which is 6 imperial fluid ounces, but a British breakfast cup, which is 8 imperial fluid ounces, or 7.69 US fluid ounces. That's right, our ounces, pints, and gallons aren't the same, in case you didn't know, or 227 milliliters. So the next time any of you out there who speak metric get annoyed that I forgot to include a conversion for you, I want you to remember this little adventure where we all learned what the f a breakfast cup is. Now, in fairness, I can't be too annoyed about this thing using a weird non-standard cup, because for us Yanks, although 8 ounces defines our standard cup, a cup of coffee is only 6 ounces. If you've ever wondered why your coffee pot has smaller than a cup cups, that's why. So we've also got our fair share of strange customary units for hot beverage purposes hanging around. And I suppose it's a fun coincidence that we've got 8-ounce standard cups and 6-ounce coffee cups, while the Brits have 6-ounce standard cups and 8-ounce breakfast cups. Actually, it's only through figuring out what this unit is on this kettle that I learned British cups are 6 ounces. What's going on there? You have 20 cups in an imperial gallon? At least our customary units consistently work in powers of 2. Until you get down to the teaspoon. Anyway, enough about strange units. How long does it take this British kettle to boil that water? Well, we have twice as much power going into this thing, so if the maths work out, it should only take about 2 minutes. And what do you know? It took 1 minute 55 seconds to hit my subjective definition of boiling, and it switched itself off at the 2-minute 10-second mark. That sure is quite a lot faster than what the other two can manage. And I suppose if you're a big tea drinking culture, it would be nice to shave a couple of minutes off the boiling time. But I still think it's kind of bonkers that shoving 3 kilowatts into a cheap plastic kettle is just a normal thing over there. But then I thought, what if we shoved 6 kilowatts into a cheap plastic kettle? Because you see, if I were to hook up an American kettle to 240 volt power, Ohm's law would dictate that it will consume twice as much current than it will from a 120 volt supply. And by also having twice as much voltage, that means its power draw will quadruple from 1500 watts to 6000 watts. And that's why I made this other adapter. This is a NEMA 620, one of the various 240 volt receptacles we have here, but which are rarely ever seen. And with a matching plug and a little bit of choppy, I can send 240 volts through these cheap kettles. And my charging station can supply up to 7.5 kilowatts, so it should have no trouble at all dealing with the 6 kilowatt kettle I'm about to make. Now, obviously, don't do this at home, for lots of reasons. One, I will be overloading the NEMA 620 slightly. The kettle's going to draw about 24 amps when the receptacle and plug are only rated for 20. But even worse, the wires going to the kettle are going to be overloaded by quite a good deal. This is only 16 gauge wire, which should only really have 13 amps pushed through it, but we're doing 24. Now, honestly, the kettle should only run for about 1 minute before the water boils, so I won't be overloading it for long at all, and I doubt any of the electrical connections are going to get very warm. But I'll be shoving a stupid amount of power through a very small heating element inside a plastic kettle, so, stuff might go wrong. Only one way to find out, though. I had a fire extinguisher at the ready and filled this kettle with my standard not quite liter at 65 Fahrenheit, 18.3 Celsius. The power switch did not latch correctly, so the start wasn't perfect, but even still, this thing got the water boiling in just 55 seconds. Not such a slow kettle anymore, huh? You'll notice the water is boiling quite violently. I'm not sure it would be safe to actually fill this thing up all the way. But boy is it quick! And sure enough, it was powered for such a brief period of time that the power cord had barely warmed up at all to the touch. Now, I decided to do this again with a cleaner start and with colder water. This time the water was 60.8 Fahrenheit, which is exactly 16 Celsius. And, well, if the colder water made a difference, it wasn't enough to tell, because again, it was violently boiling by the 55-second mark, and the kettle switched itself off about 7 seconds later. So, we learned a few things. 1, this does indeed work to make a stupidly fast kettle. 2, it's probably not safe to fill this up with any more than a liter of water, or else it'll probably throw boiling water out of itself. And 3, it survived long enough to do the test twice. But then I noticed something. Long after it had switched off, this steady stream of bubbles was coming up from where the heating element is bonded to its little support bracket. These bubbles kept going for several minutes, but there were no signs of an external leak. I thought it might be possible that a pinhole leak in the heating element had formed. See, everywhere else on the heating element is completely submerged in water, which will do a great job taking heat energy away from it. But that little connection point there might have stayed dry enough for the heating element to melt a small hole in itself. And those bubbles might be the result of air inside the heating element being displaced with water. And if that is a leak, it would be very dangerous to use again. I decided to let this sit overnight full of water so I could investigate this later. For now, I had another kettle to test. This one has its heating element bonded to the bottom of its stainless steel interior, which is a very common design. It can apparently handle 3 kilowatts without an issue. But what about 6? Well, again, only one way to find out. This kettle also only needed about 55 seconds to get the water boiling, but the water inside was boiling much more violently than the last kettle. You can quite clearly see the steam, which activates the auto stop feature, flying out near the power switch. Yeah, in case you didn't know, there's a bimetallic disc down here which will snap and shut the power off once it gets hot. And it's this tube here at the top which will direct steam down to that disc once the water is actually boiling that makes the disc snap and shuts off the kettle. Steve Mould taught me that. I picked the kettle up after it shut off and felt the bottom of it. To my surprise, it wasn't really warm at all. The electrical contacts were quite hot, but it didn't seem like the plastics had gotten any more than slightly warm. Water is really good at absorbing heat energy, but I figured the embedded heating element would direct at least some of its heat downward at the base. If it did, it was hardly noticeable. But that's where the good news ends. I tried to do this again and discovered it ain't working no more. The neon indicator in the switch was still lighting up, but no more boily-boily. So this was a very fast kettle. Once. Which is honestly what I expected. I figured these things would have some sort of thermal fuse which will blow if it gets too hot, like, for instance, if you switched it on without any water in it. And since this one only has the water on one side of the heating element, it stands to reason that 6,000 watts of power simply got the fuse too hot. But I wanted to know why exactly it failed, and with the other kettle's mysterious bubbling, there were now two things to investigate. First, if this kettle has a thermal fuse, it's integral to the heating element. I don't see any sort of separate component, and when I checked the heating element with an ohm meter, it shows either open circuit or quite a few megaohms. However it blew. The water simply couldn't pull the heat away quite as fast as it needed to, and this burnt itself out. But nothing down here seems like it got very hot. All the plastic looks undamaged, and I sure didn't smell anything during the test. That doesn't really matter, as it's still broken, but honestly, I expected a little more carnage. And now to see if this heating element was actually filling up with water. I removed it from the kettle and then used a Dremel tool to cut a slice through the heating element. I found absolutely no signs of moisture, and I even heated it up with a torch to see if any steam might come out. So I was apparently chasing a phantom there. That was probably just a nucleation site of some sort. However, cutting into this revealed that the magnesium oxide, which fills the tube and maintains an insulating gap between the electrically conductive nichrome wire in the center and the steel sides of the tube, appears to have fused together. The last one of these that I cut through had the magnesium oxide escaping like sand, but here, it's now all quite solid. I couldn't bend this any more than you see here because the tube seems to be filled with solid rock now. And honestly, that makes sense. The actual heat was coming from that nichrome wire in the center of this tubing. So while the water could do a great job keeping the exterior of the tube relatively cool, the inside of the tube was getting stupid hot. Just for comparison's sake, the 7.5 kilowatt shop heater, which started this project, spreads those kilowatts between 6 heating element sections. This little coil here is about as long as just one of those, but it was producing nearly as much heat as the entire heater does. If we could have seen the insides of the tube while it was on, I'm sure it would have been glowing quite brightly, and I doubt this would have lasted more than a few more cycles. I was tempted to get another one of these kettles to see how long it might last, but that would have been effort, and I already feel bad enough for murdering 2 of them. So what have we learned today? Well, British kettles are indeed quite fast, but hook an American kettle up to 240 volts, and it's way faster. Once. We also learned what a breakfast cup is. And we learned that Leviton makes this thing for some reason. Now, if you live in North America and actually wanted to have a 3 kilowatt kettle, one way you could do that is to ask an electrician to install one of these NEMA 620 receptacles in your kitchen. That's a bit easier said than done due to the requirement for GFCI protection in kitchens and the need for 2 free slots in your breaker panel. But with the appropriate breakers, it can be done safely and to code. That will allow you to use 240-volt appliances with a relatively normal receptacle and not one of our various terrifying monster plugs. The next part, though, becomes some flavor of sketchy no matter what. I cannot find any 240-volt kettles for sale here, which means you'll have to do what I did and import a British or European one, then chop off its plug and wire it to one of these. And the trouble there is, again, our split phase power. Any kettle you might import will work just fine, but the neutral wires inside of it will not actually be wired to neutral any longer. They will be live at 120 volts to ground. Whether that actually creates a safety hazard depends on a whole bunch of factors, and to be honest, since not all plug standards in Europe are actually polarized, I feel like most designs out there would be fine, but you will be committed to using an imported, modified appliance that you stuck a different plug on, and insurance companies may not like that so much. So keep that in mind. If, however, you've got one of them fancy induction stoves, then any ordinary stovetop kettle, that's compatible with induction cooktops of course, can be just as fast as this British kettle. In fact, possibly faster depending on your stove. I am talking proper stoves though. Those plug-in induction hot plates are limited to the same power as a plug-in kettle, so don't expect those to save you any time. If you've got a built-in cooktop or range with induction burners though, a stovetop kettle should be wicked fast. And you get the benefit of a whistle. What's not to like? Actually, while I know it's not really saving me any time, I have switched to a stovetop kettle, which I used with an induction hot plate. I have a conventional radiant stove, which honestly, I enjoy using more than my induction plate, mainly because it has real knobs that are actually infinitely adjustable. But when I'm bringing water to a boil, the induction plate is significantly faster. So, since I keep that thing next to my stove for making pasta or whatever, rather than take up even more counter space with a plug-in kettle, I just leave one of these things on there. But now, if I need to boil 8 breakfast cups of water even faster, I'll just head out to the garage. Why am I doing this? Because of our 120-volt household voltage and... Oops. Could have done the sensible thing, which would be to build an adapter like this with a NEMA 620 receptacle and then cut the end off of this cord. Well, we're having a hard time with this line today. First, if this kettle has a thermal fuse, I'm trying to pry it open. Oh, I screwed it back together. I forgot I did that. Did I not? That means I have to take it apart again to film the...